This is mostly section 14.4, but there was one problem in 14.3 that I wanted to go back to. So we'll start off by showing you that. 14.3, number 55, asks for all the second partials. Z equals y over 2x plus 3y, treated as y times 2x plus 3y to the negative 1. So z sub x, partial with respect to x, is negative y, 2x plus 3y to the negative 2, times the derivative of the inside with respect to x, which is 2. So negative 2y over 2x plus 3y squared. Or negative 2y times 2x plus 3y to the negative 2. That's probably easier to take the next derivative. Z sub y, so I'll do the quotient rule. Bottom times the derivative of the top with respect to y is 1, minus the top times the derivative of the bottom with respect to y, 3, all over 2x plus 3y squared. A little bit of cleanup. You see the 3y's cancel out, so 2x over 2x plus 3y quantity squared, or 2x times 2x plus 3y to the negative 2. So z sub xx means I take this z sub x and differentiate with respect to x. Okay, so I want to treat it like so, which means this is a constant. So negative 2 times negative 2y is a positive 4y, 2x plus 3y to the negative 3 times the derivative of the inside with respect to x, which is 2. Clean it up, 8y over 2x plus 3y cubed. Z sub y means I differentiate this with respect to y. So negative 4x, 2x plus 3y to the negative third, times the derivative of the inside with respect to y, which is 3. Clean it up, negative 12x over 2x plus 3y cubed. And then z sub xy or z sub yx, you can either take this thing and differentiate with respect to x, or take this thing and differentiate with respect to y. Either way would work. Okay, so looks like you end up with 2x times negative 2, 2x plus 3y to the negative third, times 2, derivative of the inside with respect to x, plus 2x plus 3y to the negative 2 times 2. So a little bit of touch up, negative 8x over 2x plus 3y cubed, plus 2 over 2x plus 3y squared. And you may leave it like that. Okay, so that was a problem back from 14.3. But now we'll start 14.4. Tangent planes and linear approximations. We just proceed pretty much analogously to what happened in Calc 1 and Calc 2. So a tangent plane. Now in Calc 1, we said tangent line quite a bit. Okay, but for z as a function of x and y, a surface, we have a tangent plane. So if you can see in light blue here, that's the actual function. You want a approximating plane, the tangent plane. That's just like in Calc 1 when you had a function, a curve, you have an approximating line. Okay. All right. So you can see that what has to be true is if you take the partial with respect to x only go in the x direction, then that looks like a straight line. So it has to satisfy what we had in Calc 1, y minus y1 equals the derivative times x minus x1. And something similar happens if you were to differentiate in the y direction. And basically, you just put them together. So here's what you want to put on your formula sheet. Z minus z0 equals fx, x minus x0 plus fy, y minus y0. x0, y0 just tells you to plug in that point. Okay, and it's very analogous if you just look at this. That's your point slope form, right? Remember from Calc 1, find the equation of the tangent to the curve, right? It was like y minus y1 equals the derivative times x minus x1. Okay, so just do the same thing where there's a x component and a y component. So z minus z0 is partial with respect to x times x minus x0 plus the partial with respect to y times y minus y0. Okay, and x0, y0, I mean, you can leave it out when you write it in your formula sheet, in my opinion, but you do have to remember this just means to plug in. So don't leave it as the expression, plug it in. Okay, that's sort of like in Calc 1, right? You found a derivative to be 2x, but then you have to plug in x equals 3 or whatever. So likewise here, you find fx and fy, but plug in the given point that you have. All right, and that gives you the linear approximation. So if you're asked to give a linear approximation, then you can see L of xy. That's just cleaning up this algebra to make it look like z is a function of x and y. Okay, and so it looks like something linear, which we like. We like linear stuff. We don't like all the other kinds of stuff. Okay, and the only other topic is differentials. And again, we proceed by analogy from Calc 1. Delta Z is fx delta x plus fy delta y. Okay, this is a definition. Okay, you probably should not use this on your formula sheet, though. It's correct, but you probably don't want to use it. Let me show you what you want to use for differential. So there's a 2-variable flavor and a 3-variable flavor. You can write this on your cheat sheet, but you might be better off putting the 3-dimensional flavor because you can always lose the Z component to get the 2-dimensional flavor. Okay, recall from Calc 1, you had dy equals f prime of x dx. It's like saying f prime is dy dx times dx, and it kind of looks like the dx's can cancel out, right? So you had something like that in Calc 1. So the total differential in multivariable dz is fx dx plus fy dy, or using the funny backward 6, the partial of z with respect to x dx plus the partial of z with respect to y dy. And this is kind of suggestive because it looks like the dx's can kind of cancel out, even though this is not really a dx, it's a backwards dx, but it's kind of like these cancel out and these cancel out. So they attribute to the change in dz, right? So this is a total differential. We had a topic on total differential in Calc 1. So this is a 2-dimensional flavor, but for the 3-dimensional flavor, you just add another variable. So you can put this on your cheat sheet. dw is partial of w with respect to x dx plus partial of w with respect to y dy plus the partial of w with respect to z dz. Again, it kind of looks like the dx's, dy's, dz's all cancel out. So you get the net change in w being made up of this part, this part, this part to combine for the total dw. Okay. So that's pretty much about it. Okay, so 14.4 page, focus here, 934. So again, for the benefit of those of you that don't have the text and aren't planning to get it, there's all that. And that. And I think the differential of the function, some of this stuff over here. Yeah, and I think that's about it. Okay. All right, number 1. Z equals 2x squared plus y squared minus 5y at the point 1, 2, negative 4. So what is the approximating tangent plane? Okay, we want to turn it into a linear expression. And here linear doesn't mean line, it just means no squares, cubes, and so on. So take z sub x, that's easy for x. Z sub y is 2y minus 5. Now I plug in 1, 2, negative 4. So plug in x is 1, I get 4. Here I plug in y is 2, I get negative 1. So by formula, z minus z0, z minus a minus 4 equals partial with respect to x times x minus x0, which is 1, minus 1 times y minus y0, which is 2. And technically you could stop there, but if you want to clean up the algebra a little bit, you're all good at that. Or write it as z is a function of x and y. Z equals 4x minus y minus 6. So this is the best approximating plane, the tangent plane to this function. So if you say to yourself, I don't want to use a function that complicated. Well, I guess this one's not that complicated, but you could have really complicated stuff. At that point, instead of using this, I'll use this plane. And it's a pretty good approximation. Okay, 5. Z is x sine of x plus y at the point negative 1, 1, 0. So partial with respect to x, product root. First times derivative of second, x cosine x plus y times derivative of the inside, which is 1, plus second times derivative of the first, which is 1. And plug in negative 1, 1, and 0. So negative 1 there, negative 1 there, and 1 there. Cosine of 0 is 1. So I get negative 1. And sine of 0 is 0. So z sub x is negative 1. Z sub y, this is a coefficient, essentially, it's a constant. So cosine x plus y. Plug in 1 for y and negative 1 for x. So negative 1 cosine of 0 is negative 1. So z minus z0, 0 equals negative 1 z sub x times x plus 1 minus 1 times y minus 1. Okay, or you can clean it up. X plus y plus z equals 0. Okay, 11, f of xy is 1 plus x ln x minus 5 at 2, 3. They did not give me the z value here, but you can just plug in to find the z. That's just like in Calc 1, right? At first, they might say, find the equation of the tangent at 3, 10. But maybe later they just say at x equals 3. They don't give you the 10, but you can just plug in to figure out the 10. So likewise here, in these problems, they give you x, y, and z, but technically they didn't have to give you the z, right? You can just plug it in to figure it out. Okay, so they give me only 2 and 3. What's the z value? Simply plug in. So put a 2 here, 2 here, 3 here. 6 minus 5 is 1, ln of 1 is 0. So z is 1. So the ordered triple is 2, 3, 1. Okay, differentiate with respect to x. Product group. First times derivative of the second, 1 over x minus 5 times y, plus second, ln x, y minus 5 times derivative of the first, which is 1. So a little bit touch up. Xy over xy minus 5 plus ln of xy minus 5. Partial with respect to y is a little bit easier. That's considered a coefficient. So 1 over xy minus 5 times derivative with respect to y, which is just x squared over xy minus 5. Plug in 2, 3. 2 times 3 is 6. 2 times 3 is 6 minus 5 is 1. ln of 6 minus 5 is 1. That's 0. So I get 6. And f sub y, plug in 2, gives me 4 on top. 2 times 3 is 6 minus 5 is 1. So fy is 4. Okay, so z minus 1 equals 6 times x minus 2 plus 4 times y minus 3. Z minus z0 equals fx, x minus x0 plus fy, y minus y0. And a little bit of algebra if you wish. Z equals 6x plus 4y minus 23. 15, f of xy is 4 arctan xy at the point 1, 1. I plug in 1, 1. Arctangent of 1 is pi over 4. 4 times pi over 4 is pi. So the order triple is 1, 1 pi. Notice again, they did not give me the z. Just plug in to figure it out. Okay, partial with respect to x. 4 times 1 over 1 plus xy quantity squared, x squared, y squared, times the derivative with respect to x, which is y. Differential with respect to y, 4 times 1 over 1 plus x squared, y squared, times the derivative with respect to y, which is x. Plug in 1, 1. Well, if I plug in 1 and 1, I get the same thing for both of them. 1 there, 1 there. So I get 4 over 2, 2 for both of them, right? Because you're going to plug in 1 here. You're also going to plug in 1 there. So 2. So z minus pi equals 2 times x minus 1 plus 2 times y minus 1. Okay, and you can clean up a little bit. Z equals 2x plus 2y minus 4 plus 5. 17 is kind of a show and tell. This is the back of the book if you're worried about that kind of problem. It's almost as if to say, find the linearization or find the tangent plane linear approximation to z equals e to the x cosine xy at 0, 0. And that's the back of the book, right? So you don't have to look on the back of the book, they give it to you. Okay, first plug in 0 and 0. E to the 0 is 1, cosine of 0 is 1, so I get 1. So the order triple is 0, 0, 1. So right now I automatically know that z minus 1 equals something times x minus 0 plus something times y minus 0. All right, partial with respect to x, product group. First times derivative of the second, negative sine xy times derivative with respect to x, which is y, plus second cosine xy times derivative of the first, which is just e to the x. Plug in 0, 0, sine of 0, 0, 0, 0, 1. E to the 0 is 1, 1 times 1 is 1. Partial with respect to y, that's considered constant. So e to the x, negative sine xy times derivative of xy with respect to y, which is x. Plug in 0, 0. I'm taking the sine of 0, I get 0. So z minus z0 equals 1 times x minus 0 plus nothing times y minus 0, or z equals x plus 1. Okay, and then finally a few differential problems. M equals p to the 5th q cubed. dm is partial with respect to p dp plus partial with respect to q dq. That's all. So partial with respect to p is 5p to the 4th q cubed dp plus partial with respect to q, 3p to the 5th q squared dq. 29. R equals alpha beta squared cosine gamma, alpha beta gamma. They want dr. So it's a partial with respect to alpha d alpha, plus partial with respect to beta, d beta, plus partial with respect to gamma, d gamma. That's all. So what's the derivative with respect to alpha? Well, that means all of this is constant. I just write down the constant, which really means just lose the alpha. So beta squared cosine gamma d alpha. Okay. Then I take the derivative with respect to beta. That's constant. That's constant. So 2 alpha beta cosine gamma d beta. And then I differentiate with respect to gamma, constant, constant. So negative alpha beta squared sine gamma d gamma. Okay, finally 31. 31, you're going from 1, 2 to 1.05, 2.1. Find delta z and dz. Delta z is the actual change in the function value. It's harder to compute in general. Dz is a little bit easier, as we shall see. So dz is the partial with respect to x, dx, plus the partial with respect to y, dy. What's the partial with respect to x? 10x. What's the partial with respect to y? 2y. Okay, now I just plug everything in. Dx is 0.05. You're going from 1 to 1.05. So the dx, which is like delta x, is 0.05. The dy, it's like delta y. You're going from 2 to 2.1, plug in 0.1. So 10 times x, which is 1, dx is 0.05, plus 2 times y, which is 2, dy, which is 0.1. Punch it in your machine as you wish, 0.9. The actual delta z is f of 1.05, 2.1 minus f of 1, 2. That's a lot harder. So plug in the x and y. 5 times 1.05 squared plus 2 times 1 squared minus 5 times 1 squared plus 2 squared is a little bit harder. Anyway, it comes out to be 0.9225, which is fairly close to 0.9, but computing dz was a lot easier, as you can see from the calculations that we have here. All right, so that was a tiny little bit of section 14.3, but mostly 14.4.